So in this video we're going to talk about something called a p-series. P-series are incredibly simple but very, very important moving forward in the chapter. So by definition, a p-series is a series for which the terms of the sequence are of the form given below. So they look like this: 1 over n to the p, where p is a constant. And the thing that's really important for you to recognize here is that the base in this exponential expression, the base is the variable that you're working with. So if this is an n series or an I series or a j series, you'll have the n or the I or the j in the base, and the power will be some sort of a constant. So it might be 3, it might be 2, it might be a half, but that's a p-series, right? When the power is a constant, when it's the same constant power for the entire series, right? And it's important for you guys to know it's very common when you're identifying a p-series to indicate the value of p. So to say this is a p-series for p equals 5, or a p-series for p equals 1/2. And I actually have some examples for that right here. So the two series that are given below would be identified as a p-series for p equals 5. That's this one, because you can see that there's sort of a 5 power that's being used here. And this one over here would be a p-series for p equals 1/2, because we could sort of think of the denominator here as the square root of n, as instead being n to the 1/2. So we have our variable as our base, and the power is some constant, and that's the p in this p-series expression. So the next question ends up being, okay, so great, we've identified this thing called a p-series. How do we determine when they converge and when they diverge? And that's what's coming up next. It's actually a very, very, very simple thing, right? If p is greater than 1, the series converges. Done. If p is less than or equal to 1, the p-series diverges. Done. I mean, there are no two ways of thinking about these things. So actually, one very easy example I could give you is the problem that we had at the end of the previous video. You guys used the integral test to show that the sum of 1 over n squared diverged. And when we actually did that, I think we actually did, it was from n equals 1 to infinity. We did the integral test, we went through this long process, and found that it converged, right? But we could just as easily have said, hey, look at this thing. This is a p-series for p equals 2, right? Now, since 2 is greater than 1, this converges. And we say, like, this converges as a p-series. And we're done. That's the end of the problem, right? P-series are very, very easy to identify. They're very simple, so we don't see them a whole lot, but they end up being used for some other things, and we'll get into that in tomorrow's lesson. A very, very common example of a p-series that diverges is actually this one. If you have the sum n equals 1 to infinity of 1 over n, this one actually has a special name. This is called the harmonic series. So that's called the harmonic series, and the thing that's important about the harmonic series is that this diverges. Right? It diverges because p is 1, and we said that if p was less than or equal to 1, the series would diverge. Now, one of the important skills that's associated with p-series is identifying when something is a p-series and when it's not a p-series. In particular, geometric and p-series can be very easily confused. So what I want you guys to do is I want you to sort of like pause the video and look at these 4 series. For each of them, I want you to identify, is it a p-series, or is it geometric, or is it something else weird? And once you've done those things, determine whether the series will converge or diverge based on the tests that we've learned. So pause the video, think through each of those. When I do them, I'm going to do them from left to right, so we'll sort of talk about them as we're going along. So you can check in at different points along the way. So this first series here is actually a geometric series. Part of the reason that we know that is that it's got a constant for the base and is being raised to a power. So what you can sort of see here is that the common ratio in this is going to be 1/3, right? The first term, well, that would be when we input a value of 0 for n. When we put in 0 for n, we're going to get 2 over 1, which is 2, right? But the common ratio is 1/3 because the n is sort of only applying to the 3. We're going to be multiplying by 1/3 more each and every time. So because of these facts, we can tell that this converges. In fact, all that we really needed was to see that the common ratio, the absolute value of that common ratio, was less than 1 to know that that's going to converge. For the next problem, we have 2 over n cubed. This is a p-series. And in particular, this is a p-series for p equals 3. And so, because of the fact that it's p equals 3, that p is greater than 1, this will converge. Right, so we have a convergent p-series because p equals 3. For the next one over, right? This one, similar to the previous one, we have a variable in the base of the exponential expression, and so because of that, this is also going to be a p-series. This is a p-series for p equals 1, and you remember we had a special name for this. This is the harmonic series. And the deal with a harmonic series is that it diverges. I mean, and specifically, when the p-series has p equals 1, we know it's going to diverge, but you could also memorize it as, hey, it's the harmonic series, I know that that one diverges. Okay? The last one that we have here, if we thought of this expression here as being 2 over n to the 1/2 power, then we could pretty clearly see that this is another p-series, and it's a p-series for p equals 1/2. So once again, because that p-value is less than 1, this is going to diverge. Right. When we're working with p-series, there really isn't any work to showing that they are convergent or divergent. They're simple series. We're supposed to look at them and very, very, very quickly know whether they converge or diverge.